pleased to have Herbert Spohn from Munich and telling us about shape fluctuations of growing droplets and random matrix theory.
Thank you very much, Tom, and thank you for this invitation. So, so what I would like to explain to you is sort of a connection between a problem in non-equilibrium statistical mechanics, which is sort of motion of fronts, and random matrix theory. I mean, you will not learn very much new about random matrix theory. It's sort of more that it's the largest eigenvalues of the standard Wigner-Dyson random matrices. I mean, like GOE and GOE, which sort of somewhat surprisingly enter into the analysis of the shape fluctuations. Okay, so this is what I'm trying to explain to you. And since I sort of assume that no one knows anything about the subject, but what I thought is I first sort of spent like maybe the first half of the talk actually explaining you a little bit what the problems are. So, you know, this is growth models, moving interfaces, Kardar-Parisi-Zhang equation. And from the outset, this is going to be restricted to one-dimensional interfaces. So the bulk would be two-dimensional, and the line which sort of separates the faces, the interface will be one-dimensional. Of course, all these things have, you know, generalizations to higher dimensions, but since we cannot do any analysis on them, I will just restrict myself to the one-dimensional case. And then I want to explain you sort of a very spectacular recent experiment by Takeuchi and Sano, who sort of make an almost perfect, you know, as much as you can judge, I mean, almost perfect realization of the theory, which you know, sort of people have developed over many years, and many of the predictions which one has made actually sort of can be very well confirmed by this experiment. And I mean, I'm certainly not an experimentalist, but you know, it's such a spectacular sort of event that I spent a little bit of time to explain you what they actually did. Okay, and then comes sort of the little bit more mathematical part, namely the issue of exact solutions of this Kardar-Parisi-Zhang equation with sharp wedge initial data. I mean, so you know, this is work which sort of was done independently in parallel without knowing of each other by Amel, Cohen, and Quassel. So that's Cohen-Toronto connection and in Munich. And I mean, the starting point is exactly the same. Eventually you have to do an asymptotic analysis, and for this asymptotic analysis we use sort of very different tools. I mean, so they use sort of contour deformation, and we are using sort of Ramanujan summation formulas in order to get a handle on this asymptotic analysis. So presumably, I will not, you know, I will just sort of scratch the surface. I will not be able to really go into much details, and maybe usually there's no time left. But if there's some time left,
can I ask you a
yes?
question here? In your work, do you use this work of Tracy and Widom?
Yeah, that's the
So
starting.
that's
The starting point. The starting point of both of these groups is just sort of it was exactly the same idea. You start from the Tracy-Widom, and you realize that there's a particular scaling which gives you the KPC equation. And then you have to do, in order to get some, you know, concrete information, you have to do an asymptotic analysis, okay? And the point is that these asymptotic analyses in the two papers are somewhat different, but the final result, fortunately, is the same, right? I would have been sort of real. In fact, when I saw first their paper, I said, no, it is different. And then, you know, you start checking, and then, of course, you realize, no. I mean, you know, we completely agree on the result. But the procedure, and I mean, you know, I mean, they have much more details. I mean, it's a beautiful paper. I mean, so if anybody wants to sort of understand more the mathematics, I think that's a good place to look. Okay, fine. So now let me try to see what we can do here. So so these are growth models, moving interfaces, and the idea that you have sort of two faces in contact. One of them is stable, and the other one is unstable. Maybe you should call it even metastable. I mean, the point is that you want to have each phase separately to have, you know, fast relaxation, and secondly, you want to have that in the unstable or metastable phase, the bulk nucleation time is very long compared to the time scale which governs the motion of the interface. Okay, so that's sort of a very generic problem. And you know, what we exactly mean by stable and unstable phases, I will give you various examples, and then I think it will be sort of more clear, you know, what we are thinking of, but it's just a very generic problem on interface dynamics, okay? And so let me sort of give the first example. I mean, this is the one which actually one understands sort of to some extent best. I mean, that's the contact of two equilibrium phases, and the standard example is to look at the 2D Ising model at low temperatures with a small positive magnetic field. You do spin flip Glauber dynamics, and the positive field sort of favors the plus phase. Okay? And I want to start already with an interface, and so what I do is I imagine that the interface is orientated along the 1-1 direction, and so here this is on the lattice, and so the interface would be just sort of the staircase. Here I have the plus phase and you have the minus phase. And when you now sort of turn on the dynamics, then of course if I'm sitting out here and wait sufficiently long, eventually a minus spin might be flipped over to a plus spin. But that's the bulk nucleation time, which is considered to be very long. And so the action is actually here at the interface. And so you see what can happen is that this spin can easily turn into a plus spin. And since I have a magnetic field, the reverse process will be somewhat suppressed. And therefore, predominantly, this interface will be moving into the along the indicated direction. Okay? And then there's a simple mapping. You can sort of turn this by 45 degrees, and then you think sort of like what is then now sort of a down line, you put a particle, and the up line you put a hole, and then you ask yourself, how this dynamics translates into the motion of these slopes. And then you see that in this particular approximation, when I completely suppress any reverse process, reverse process, I mean that, a plus which is sitting at the interface will flip into a minus. Then you see that it corresponds to just particles sort of jumping forward, and you start with initial configuration, which we usually call the flat initial condition. It's just alternating 0, 1, 0, 1, 0, 1. That's a model which can be analyzed. Actually, it's quite recent. This is work of Borodin, Ferrari, Sasamoto, which sort of like 3 or 4 years ago. And the case which can be studied it has been studied in much greater detail is another geometry where you imagine that you have sort of like a quadrant, and you put down here the plus one. So here, this is the stable one. And then you have here the minus phase. And then you see what happens is that the first flip which can occur is the one over here. And then you can flip further like this. Okay, and you can flip further. Okay, and this way you sort of generate sort of like a fluctuating interface, which now has, because of this boundary condition, on a macroscopic scale will be curved, right? And so this is why we call this the droplet geometry, or the curved initial condition.
Like RSK, is it?
Yeah, sure. It's very much related to RSK. Yeah, that's correct. Yeah, and okay, this one is sort of more difficult.
What's RSK?
Robinson, Schenstedt, and Knut. Robinson. No. Yeah, that's the longest increasing subsequences. That's right. Yeah, no. This model. There's another model which is sort of even isomorphic to the longest increasing subsequence. This one is sort of close to it, but not exactly identical. Okay, fine. So that's one example. Then there will be. Let's see what I have here. Okay, so this other example will be that this could be non-equilibrium steady states. In fact, that's actually what's happening in the experiment, which refers to turbulent pneumatic liquid crystals. Then there are Gross models, which are sort of of a similar type. If you sort of think just in terms of the interface, so you can imagine that you have sort of some carbon configuration, and you sort of drop material downwards, and whenever you first find a whole edge of touching, then you simply you just attach your extra particle over here, and then you sort of get this object growing. This is sort of not so easy to analyze because you have these overhangs and there might be holes and all kinds of things. So there's a simplified version of that. It's this model which is actually completely identical to the longest increasing subsequence problem. And so what you do here is that you imagine that you have an interface which is now living over the real line, actually. So this can be at any point, so to speak, but you have only these up and down steps. The way how these things are moving in time is that you have a deterministic lateral growth. These are just these blue arrows, which means that this is moving with speed 1 to the left, and this is moving with speed 1 to the right. Now, at some point, they might meet, and then they simply sort of coalesce. So if this is moving here, then eventually it will just fill up that layer, and the two steps have coalesced. But then on top of this, you put a random nucleation, which are these red points here. So you do this randomly in space and time, and once you have generated this, nuclei, this little spike here, then it will immediately expand with unit velocity to the right and to the left. Okay, so that's another. That's open ups and just and then they're all. It's always unit speed. So there will be never any. I don't run into any sort of configuration where I don't know how to continue my dynamics.
How come why don't you have overhang? You could have. You can't
No,
have
because
overhang.
this one, yeah, because this one is moving exactly the same speed as this one, so it will never generate an overhang.
You avoid the overhang.
You just avoid the overhang. And this model is really completely isomorphic, okay? So another one is sort of a supercritical contact process. So you imagine that there's some infection which is spreading, and let's say the rule of the infection is that, you have already sort of a particular set of infected sites, and then you simply declare that all neighboring sites can be infected, and you can do this with various rules, but in this Eden model, what you simply say that is you do the sort of in discrete time steps, you sort of indicate all the possible boundary sites of the current cluster, and then you fill in the next step with equal probability. Okay, so that's sort of one.
You just erase the X and put in the
put in particle, but there will be many sites, and I just pick one at random. Okay. And here I have a picture which is quite instructive for this type of thing when you do this on the continuum. So now the contact points will be a line, and you just take sort of the uniform measure on that line. I mean, so here I have all this, red ones are, disk at which I can have a possible contact. So it's a sort of line consisting of broken circles. You just put the uniform measure, and the next line you randomly pick one, maybe this one, and you add.
Picking them at the boundary, not picking them inside.
Well, now inside I cannot do. It's already, there. If there would be a hole, then I also put it inside. Yeah, sure. Okay. Everywhere I can put. Okay. And now you see, I mean, this picture is interesting because you see that first of all, this is totally isotropic. I do this in the continuum, so on average it will be a circle. But you can also see that there are very strong shape fluctuations, right? And so it's the shape fluctuations which you would like to understand. All right. Okay, so let's see, what else do we have as example? Okay, so now comes sort of the KPC equation, which is sort of, was, it's over 25 years ago this was proposed, exactly for that purpose. And, this sort of comes more from sort of statistical mechanics field theory, and these people were sort of, not so terribly happy with having such a discrete model, so you try to write down the continuum equation, okay? So what they posted, so this is, very famous work by Kardar-Parisi-Zhang, and what they did is they postulated that you have a particular height profile, so overhangs and these kinds are ignored, so your interface is a graph of a function, and since we are, restricted to the case of the line, so the x will be just on the one-dimensional line, t will be your time parameter, so that starts at 0 and sort of it's evolving in time. And then they just wrote down this particular equation here. I'm explaining a second time, the various terms. But I guess the most important thing to notice is that, this of course would be just an ordinary deterministic PDE, but now they add to this equation white noise. So it's a stochastic partial differential equation which we have to deal with. Okay. And so the W is just sort of standard white noise. I put here all the coefficients in this equation sort of to 1, to make sort of the structure more transparent. But there's a lot of scaling invariance. So eventually, in fact, this equation really has only one single parameter, which is the time. Okay, so the crucial observation of Kardar-Parisi-Zhang was to say that, when I look, let's say, at the change of the height function at a particular point x, then it will depend on the local slope. And in fact, it will be depend non-linearly on the local slope. And then somehow you sort of argue that you could imagine that you put here more general functions. Instead of putting the square, you can take the force power and things like this. And then there's sort of an argument that this shouldn't make too much difference in the sense that the large distance behavior would not depend on what particular power I put, but I must have a nonlinearity. Okay. All right. So how do you get this term? Well, there's sort of very simple, which you find out in the original paper, but it's a useful argument to sort of to remember. Is that imagine just like in the case of this isotropic growing Eden cluster, I have an isotropic growth velocity. So this means that if I'm in the plane, you see, I'm really in the plane like this. I'm going, with unit velocities in all possible directions. So a circle would just expand with a constant velocity. Okay, and now I'm representing this situation in the hx frame which is sort of given to me. And now you see that if I place something which has zero slope by this amount and something which has non-zero slope by this amount, this corresponds to isotropic growth. If I look in the hx frame, of course, I will have an increased velocity. So, if you want to, from that perspective, it's a purely geometric effect. But of course, the nonlinearity is then, of course, if I do it isotropic like this, then the nonlinearity is somehow hidden somewhere else, right? But so here it's just sort of a simple way to see this nonlinear term. And when you do this computation for flat profiles, it's easy geometry that you see that the h dot is equal to this sort of relativistic dispersion. So it's 1 over the gradient squared and square root of that. And then, you do a Taylor expansion, and the one you can absorb into moving the frame of reference. And so the first leading term would be the one which I've written. But of course, the claim is that if I put the square root, I will see the large-scale behavior. That's the claim. I mean, this certainly has not been proved. Okay, and now, so KPC equation is another, if you want, is another model, sort of on equal footing at that stage with all the other models which I have mentioned. Okay. And which model you sort of eventually look at, that's a question of taste, and on which you can do some analysis and these kind of things. Anyway, so what you would like to understand, of course, the shape. I mean, that's sort of more sort of the fact that it's a circle or some other shape. But the real thing, of course, is that one expects or one hopes that if I look at the fluctuations, they are universal in the sense that they do not depend on the specific model I'm actually studying, right? I mean, so particular, would be the hope that this particular stochastic PDE and this simple type of sort of more discrete type of growth process would actually have the same large-scale behavior. Okay? So the interest really comes from this issue of universality. Now, I should mention at that stage that.
So what's supposed to be universal here?
Well, I mean, I'll explain it much more. No, just I mean, universal is supposed to be the statistics of the shape fluctuations, but I will explain it in much more detail. I just want to emphasize at that stage that this issue of universality in this field is not clarified at all. I mean, the point is that we have a number of models. I mean, growing number of models. I mean, slowly increasing function of time, for which you can sort of do some rather detailed analysis, and you confirm that there are these universal things. But there's nothing like anything sort of.
In the sense they all agree with
all agree with each other. That's right. In that sense, right? But there's no theorem. If I take one particular model, and if I mean, for instance, the theorem of the type, I replace the square by this function, and I get the same large-scale behavior. I mean, this is completely out of reach at the moment. Okay.
Or you change the white noise to some color noise.
Exactly. You can do many changes, and presumably these things are very robust. But I mean, okay. I mean, this is simply, if you want to do really proofs, it's out of reach. I mean, I think the evidence is quite overwhelming. But okay, now let me come to the experimental realization. So that's an experiment by a young fellow at Tokyo University. That's Takeuchi. I didn't put the name here again. Anyway, so this is an experiment by San and Takeuchi. And what you do is you have a thin film of a liquid crystal which is turbulent. And the point about turbulence is that if you just have thermal fluctuations, they might be too little to actually observe these effects. However, when it's turbulent, then you have more fluctuations and you can more easily see. Okay, so you should think this is sort of like just two plates. They have rather small distance, and this liquid crystal sort of consists of little rods, and on average they are sort of pointing normal to the two plates. And another very important point. So it's sitting at an oscillating external field. I mean, this is what produces the turbulence. The cell size in the lateral direction is sort of like 2 centimeters, so you can hold it in your hands. You don't need any sort of, it's in that sense, it's a rather low-key experiment. And by the physics, it's in-plane isotropic. Okay, so when we will see a droplet growth, the macroscopic shape necessarily must be a circle, just because that's how the physics is. I mean, there's simply no direction which is singled out. Okay, and now you put this sort of, the point of these numbers is that you put this on a very particular point in this non-equilibrium phase diagram, and you have two phases. I mean, they are called dynamical scattering modes. One is this is phase 1, and that's phase 2. And the one is the phase 1 is the unstable phase, and under transmission of light, you just see it as gray. Okay, and then you have a stable phase, which is called phase 2. And this has a lot of topological defects which sort of prevent scattering of light. And when you look in transmission, you just see it black. So you can very easily distinguish by optical means between the two phases. Okay? And the point is that this DMS1 phase has long bulk nucleation time. So in fact, I went all the way to Tokyo in order to see this experiment. What you can see is that you just look at your screen. I mean, you will see the metastable phase just gray fluctuating in front of you. And then you wait for like 2 or 3 minutes, and then there will be a nucleation coming simply from the boundary of the cell, right? I mean, so that's what's happening. Okay. Now you want to do this growth problem, and so you take a laser and you make a point seed of the stable phase, which will then grow as a droplet. And since we want to see the difference between the curved and the flat case, you can also ask your laser to make a line seed, and this will grow then, in both directions. This is your line seed, and will grow this way and will grow this way. Okay. So let me show you the picture. So this is the point seed picture, and it's very similar to the other pictures I showed you. You see the time scales. I mean, they're quite sort of okay. So what you do is you just record this. I mean, then there are little overhangs actually if you look closer. I mean, so you sort of produce your radius as a function of the angle. That's x and time t, and then typically you would do an analysis of this fluctuating radius. I will come to that. But these are the raw data which you actually have. Okay. Okay, now I want to sort of explain you one more thing why, if you just look at this, you will regard this as totally uninteresting. You will not see anything whatsoever. Okay, so you need a theory in order to understand these pictures. Okay, and that's of course, based on this early work. Namely, what I want to do is I now want to look at one fixed direction. I mean, for instance, I could always look here in the 2 direction, or in the flat case, I could fix this point. I want to look at the height above this specified point. So the point is that you see of course you can ask more complicated statistical questions, but here we are just asking for the fluctuation of a scalar quantity, and we do this for each time. So in this field theoretical language, you just look at the 1-point function. I mean, okay, so 1-point distribution function. Okay. Now what the KPC scaling theory tells you is that if I look at this h of t, so this is now just a scalar function of t, then in the long time limit, so the leading term, of course, will be linearly in t because it's just growing. Okay? Well, now what KPC predicted is there will be a sublinear term which has a size which goes like t to the 1/3. Okay? And then there will be a random amplitude. And of course, the whole point is sort of actually computing or finding out about this random amplitude. So what you measure in the experiment is this random amplitude. Now you see, you always have to distinguish between quantities which depend on the system and which are universal. This one is universal. I mean, also the 1/3 exponent, but these prefactors are non-universal. And so if the system would be not isotropic, and if I would, sort of mix data from various directions in order to get a better statistics, you would average over things with different prefactors, and then you just don't see anything. So it's very important that in system, because of the physics is isotropic, you know that these things do not depend in which direction you're actually looking at. Now, how do we know these 2 coefficients? So you see, the way you do the experiment is that you have all this data, and the first thing what you do, you have to determine these non-universal quantities. You see, if you do a naive statistical analysis, for instance, here you see this is the velocity after a very, very long time. So if you just naively would subtract the average, I mean, you wouldn't see anything. Okay, so it's very important that one does the correct analysis. So now let me just sort of recall these 3 points. I mean, there are 3 non-universality quantities which you have to compute. One of them is the growth velocity, which is sort of easy because you just wait long enough, 40 seconds, and then you sort of from this you compute what is your radius at time t. That gives you sort of at least a reasonably good estimate for the v infinity. I mean, this is sort of determined with rather high precision. Then there's this coefficient C2, which is a little bit more complicated. I mean, first of all, it enters sort of the nonlinearity, which is usually called lambda. Now, because it's isotropic, this was this little computation I showed you actually. You find that the lambda is actually equal to the v infinity. So this means that it's very important that now you have, instead of 3, you have only 2 parameters. Okay, so this is very nice. And then there's another one which is more complicated, which sort of is related to stationary height correlations at small distances. So that's already theoretically a more complicated object, and also in terms of determining, I mean, the C2 is sort of a little bit has less accuracy than the one. Anyway, you do this very carefully, you fix it, and then you have no adjustable parameters anymore. everything, all the scales are fixed now. All right? And then on this scale, you do the plot. And this is just sort of to remind you of at various times, I mean, how this droplet is actually growing. And then you do a statistical analysis, and what you find are sort of, I just, want you to concentrate on two pictures. I mean, so first of all, this one. So what you do here is, so this corresponds to the droplet growth. So you determine this random amplitude psi. I mean, so that's just a distribution of this random amplitude. I mean, so all these other things have been taken care of, and all what is left is this random amplitude. Okay. So this is plotted here on a logarithmic scale. And so you have sort of, I mean, he does the experiment sort of like 1,000 times, and then you do all the averaging along the circle. So you have a lot of statistics, and so you see that this is a logarithmic scale. So the probability, that's the probability distribution of this random amplitude. It goes down to a level of 10 to the minus 4. So it's actually quite precise. And what you see is this dotted line here is the distribution of the largest eigenvalue of a GOE random matrix. So that's the famous Tracy-Widom distribution at beta equal to 2. And you see the dotted lines here, and the theoretical prediction is that for a long time this random amplitude is actually exactly the GOE, and you see that it's rather close. There's a little offset here, but that's just sort of because you cannot look at infinite times. Okay? All right, and now you do the same experiment for the flat interface. So now typical configurations look like this. And
1/3 worked out correct.
Oh yeah, the 1/3. I mean, there are other. I mean, I didn't put in everything, but the 1/3. I mean, you see very, very, very clearly, right? So now I'm looking even finer. You see, I'm not just looking at the 1/3. I'm looking actually at the random amplitude. No, the 1/3 comes out very nicely. Okay, now you see that this is displaced a little bit. I mean, you might think it's the same, but it's not really the same. Here it's compared with the GOE largest eigenvalue. So that's Tracy-Widom beta equal 1 eigenvalue distribution, and you see that it's sort of more or less the same feature. It's a little bit displaced to the right, and otherwise it reproduces, down to a scale of almost 10 to the minus 5. It reproduces this distribution. Okay, so that's experimentally sort of an absolute spectacular confirmation.
Beta is compared to what matrix? What is compared to GOE versus GUE?
Okay, so this dashed line is computed by looking at a GOE, so that's beta equal to 2, n by n random matrix.
Which experiment do you assign? How do you look at the experiment and decide whether it's going to be GOE or GUE?
Oh, because we know that in the droplet case it must be GOE, and I will show you. I mean, there's a theory which tells you that. Oh, this was the question. Sorry. Okay. So no, I mean we know that in the droplet case the prediction already on discrete models was that it should be GOE. In fact, this is already the longest increasing subsequence. You have to make the connection.
You start from a drop or a flat. Right? It's a question of whether you start from a flat interface or a drop.
Yeah.
You'll get
So let me So I mean the assertion is that whenever you have sort of this droplet geometry, then the 1-point fluctuation should be like GOE. Okay. Whenever you start from a flat, then you remember actually that it's flat. That was, whenever I give these talks to sort of more physics audience, this sort of usually they regard this as the most surprising point, that the system does not forget the initial data. It still remembers a little bit, and so when you do the flat thing, then you see the GOE. Does that answer your question? Okay, and then there's another thing which presumably I don't have time to really go into, but I emphasize because it sort of comes from this exact solution, is that once you have all this nice data and you see this little offset, I mean, you can try to analyze more precisely what is that offset. Okay, so you look at the cumulants. I mean, on that scale, you look at the cumulants of your measured data, and what you find is sort of what you can also sort of almost see with your naked eye is that the higher cumulants, this is 20 seconds, so the higher cumulants sort of rapidly sort of decay to almost 0, whereas the first cumulant, that's just the offset, will decay slowly, and then you determine the power law, and it decays like t to the minus 1/3. Okay, so you should think that sort of the leading finite time correction just means that the distribution has already the correct shape, but then it will shift slowly, and it eventually sort of decays to the final Tracy-Widom distribution with t to the minus 1/3. This is something which was not known before. This is something which does come out of the exact solution.
I'm interested in one point.
Yes.
In Tracy-Widom, I think they defined their distribution incorrectly because they introduced this term which is sort of, I think this is probably connected with the skewness. You know what I'm talking about? they
Yeah.
don't make the mean zero.
No, no, it's not mean zero. You see,
Finding that,
sure, that's very important. It's not mean zero. So
that number comes out. In other words, that's a universal constant which comes out as well from your analysis.
yeah, sure. Let me explain. That's a good point. So let me just explain this in this formula. I mean, just read this formula of random matrices. You see, this would be T is equal to n. I mean, so and H would be the log. Okay, let me make a picture. I mean, then it's maybe easier for the others to follow. So here you have your random matrices. Okay, so this is somewhere 0, and I'm using a scale where the typical distance between eigenvalues is 1, right? And then from the semicircle law that for large n the edge is exactly at 2n. You see, that's exactly this term here. And what I'm emphasizing, you should not take any, don't subtract, take the asymptotic velocity, take the edge as given by the semicircle law. And relative to that edge, I mean, you will see now a distribution which has sort of a non-zero mean, and okay. So the next eigenvalue will be sitting somewhere over here, and this goes like n to the 1/3 times the Tracy-Widom, right? And so it's complete analogy to what I've written down here for the height. Yes, Michael.
There's a difference between the circular and the flat.
Absolutely, yes.
Then if you think of a circle and you count time by the total number which is deposited around, there would be fluctuations on the mesoscopic scale between the number which is deposited into a particular angle versus other angles. Wouldn't this somehow contribute to the offset and other things? In other words, the T to the 1/3, what is the relevant time when you're looking at a particular direction?
Well, it's given by it's.
Around the circle, or just something in a small angle around the direction?
Well, no, I mean here for this thing, I mean I mean when you take the data, you look at one particular fixed direction, and that's it. So no angle.
For example, to fluctuations between the number of points which go in the northern versus southern.
Fine, but the theory is that I mean you know what the origin in your frame of reference is, and the theory tells you what you should do is you should look at one particular. I mean for that equation, I mean the theory simply tells you look at one particular direction.
Yeah, but you found an offset in the theory and the experiment.
No, but the offset just comes from the fact that I mean I have not really I mean this random amplitude of course is time dependent, and I simply have not reached sort of the asymptotic limit. I mean if you could do the experiment up to instead of 40 seconds you could do it to 200 seconds and you would see no offset anymore at all. So okay, all right. So let's see. So now we have okay. So now let's come to this KPC equation. So let's see. Okay, so we're doing not so badly with time. Okay. So now this sort of switching of gears. I mean, so the next thing will be sort of concentrating exclusively on the analysis of the KPC equation and sort of trying to confirm some of the claims which I made before and sort of explain you a little bit what you can actually do. So here I just repeated this equation. I mean, so I had this before. All the coefficients are equal to 1. But now I want to do a specific initial condition. I mean, that's an evolution equation. I have to sort of tell you how to start it. And what I want to do is I want to start with what we call the sharp wedge initial condition. So it's a sharp wedge which sort of roughly looks like this. And if you write it in formula, eventually, I mean, we will take a limit where, this needle becomes infinitely sharp. And you will see it's not very difficult to understand why we actually need that, okay? All right, and now you wonder how this is going to evolve in time, and it's not very hard if you just sort of, okay, so maybe I should say one word. You see, if you forget about the W, and then if you differentiate this one time, you get the Burger's equation. Dissipative Burger's equation, and then taking the slope means that I'm just starting a Burger's equation with a huge jump, right? And so what you will see is that immediately this sort of flattens out for the signs which I picked, and so what this means that if I just study the deterministic evolution, that will be completely dominated by this term, and what you will see after a short time is on the average a simple parabola. Okay, and when you do this analysis a little bit more complete, I mean, you find that so it's a parabola which sort of scales properly with 1/t, so the curvature sort of becomes flatter and flatter, and then in fact you find also an offset which is also proportional to t. Okay, so this means that if you think back, to such kind of a picture, what we do here actually, you know, just in the spirit of KPC, what we claim is that if I look at the little top part of this droplet, of course, it's not the whole droplet which I can cover, but the top part of the droplet will be very well covered by analyzing this equation, right? And since that's all what we want, you know, the thing which they measure in the experiment would be, for instance, you know, this fluctuating point. I mean, right? I mean, if I look in this particular direction, so this means in this picture that I'm looking sort of in the two direction, then it's the question, how does this point fluctuate? Right? And the assertion is that it has a piece which is linear with a negative coefficient in this case, you know, and then there will be a coefficient which is going like t to the 1/3. That's what I put here. And if I wait long enough, well, I'm here, of course, okay, we don't know yet, but anyway, so in spirit, if I wait long enough, it should be Tracy-Widom. Okay?
And if I pick any other, if I draw another line, let's say parallel to the, I will see the same.
Yeah. So that's something which you can check, in fact, directly from the equation. That if you subtract this parabola, what you actually see is something which is a stationary process, and therefore, whether I look here or whether I look here, I will see the same statistics. And in fact, the other prediction is, I mean, those people who know random matrix theory, if you look for long times at the fluctuations of this line, I mean, you will see the top line in Dyson's Brownian motion. So you know, so that's a one-to-one correspondence. So the connection to random matrices is actually much more, you know, a little bit more deeper than what I can actually explain here, right? But that's the effect. Okay, and then you know, then there are transverse correlations which go on the time scale t to 2/3, and what we expect, of course, is that we should see GOE statistics in the long time limit, and then of course there will be finite time corrections. Okay, so now let's see what we can do. So here's the theorem. I mean, there are various versions of it, but I like this one because, you know, it's sort of, it's not written in any of the, well, actually it's written in one of our papers, but anyway, I mean, it sort of has the advantage that it's sort of presumably the most concise formula. And so I take this KPC equation with sharp wedge initial data, and then the claim is that I can compute this very particular generating function. So this is now the height at time t. You see, I have done here these abstractions, and this parameter s is sort of the parameter of my generating function. So this is a function which sort of, you know, has sort of the s shape. I forgot already. I always forget whether it goes this way or the other way. And the parameter s, I mean, just sort of shifts this back and forth, right? I mean, so if I tell you all this expectation, of course, you know, the probability distribution which I'm after is determined. And in fact, historically it went differently. I mean, you know, we first computed the probability distribution, and from this we actually obtained this generating function, right? Okay. But it's identical information. And the assertion is that this generating function is given in terms of a Fredholm determinant, and it's a determinant which is for a linear operator which is defined on the Hilbert space L2 over R. This P0 projects onto the interval of 0 up to infinity, and KT, you know, has an explicitly given kernel, which actually has a rather simple structure. Namely, you see here sort of these double area functions, which you sort of know also from you know, other parts of random matrix theory, and but then it's somehow smoothened with this particular sort of factor. Okay.
You actually show the satisfies the differential equation.
No. Well, you see, I mean, you know, it's only very partial information about the. I'm coming back to this issue, you know, what we even mean by the equation, right? And so it's just sort of, you know, I'm telling you, you know, I'm claiming a theorem about an object which I haven't even defined, right? I mean, so, but it's okay. I'll come back to that. I just want to make sure that you understand, you know, what the punchline is. Okay, so there's this kernel, and you know, so now what you from this, you know, you see that I get sort of these deterministic terms. I mean, you can read off, and then of course now there's a random amplitude which I defined here, which now depends on x and depends on t. In fact, it's a stationary process in x. I mean, so you know, in there, but you know, as written like this. So and then of course what we can sort of see from these formulas, because I have the 1/3 peering, is that this random variable must be of order t to the 1/3. Well, and then what you do is you sort of do the scaling. I mean, so you know, we always argue that you know, it should be of order. This quantity should be of order t to the 1/3. So I multiply with t to the -1/3, and then the claim is that the limit as t going to infinity actually does give you the Tracy-Widom GOE distribution. And since for this part it's so easy, let me just give you actually, I mean, you know, I mean really the proof. I mean, you see in other models it's much more complicated, and of course all the work goes into actually doing this computation. But once you have this, I mean, this fact is an easy consequence. Okay, and so let me just show you. I mean, you can see it more or less immediately. I mean, so I do the v-scaling, and then you see that this object will go to a step function, and when I do the v-scaling, then you see that this one also goes to a step function. It just becomes the integral from minus infinity to 0. And if I combine both observations, then you see that that the limit as c goes to infinity of this v-scaled amplitude. Now I put here sort of the origin goes to this particular limiting kernel, and that of course is the one which you know from random matrices. I mean, so this kernel is the so-called area kernel. Here it's written down explicitly. And you can also think of this, which is actually quite useful, you can think of this as a spectral projection. So you introduce this, what I like to call the area operator, so that's just, I guess, Schrödinger equation in one dimension with a linear potential. And then you realize that I mean, this commutes with the area kernel, and in fact, the area kernel is nothing else but the spectral projection to all values of h which are negative, right? I mean, so. Okay, so I guess the only thing which I want to emphasize is the fact that in the long time limit you get the Tracy-Widom distribution. I mean, from this formula it's very easy to conclude. I should say, you know, when we started to work on this, I mean, we were oscillating back and forth. You see, I mean, at some point we got formulas and said, look, it will never go to Tracy-Widom, right? I mean, there was no guarantee a priori why this continuum equation, you know, why it really should have, you know, exactly the same universal behavior as the discrete models, you know, despite the fact what everyone says. I mean, you first have to make some more serious analysis. Anyway, so it does come out, and in this formulation it comes out very easily. Okay, so now the next question is, I have to sort of say a few words about, you know, how one actually, I mean, you know, which way do you even, you know, approach this problem. And the point is that what you want to do is, okay, so the, let's see. Okay, so I mean, the main tool which you observe, which everyone in this field observes, is that you first use the Kohl-Hopf transformation in order to construct the solution. Okay, so I mean, let me try to say this maybe more clearly. I mean, so you have this KPC equation. You see, the ideal thing would be that you have some sort of solution theory of this equation. Okay, now this is not available, and the reason why it's not the reason why it's difficult. I mean, maybe I can flash the equation back in. Is that if you just solve the linear equation, then you see that in X you will get typically a behavior which is like Brownian motion. Okay, so if I just solve the linear equation, and if I look at fixed time and I look at the profile as a function of X, you will see sort of, it's a continuous function, but you will see sort of, you know, this cusp type of behavior of Brownian motion. So now if I'm asked to differentiate this function, you know, of course I can still do it, but, you know, I get something which is already a distribution. And then if I'm asked to do the square, then you are stuck. Okay? And there's no solution theory to this equation whatsoever. I mean, there are people, I mean, Heyer, for instance, I mean, he's one of the persons sort of having some theory of rough paths. I mean, he believes at some point we'll be able to give a solution theory, but it's not something which is available, actually, okay?
What's his name?
Martin Heyer, I mean, from Warwick, I mean, so same one, you know, who worked with Jean-Pierre Ekman about this heat flow problem, and so on. That's right, that's exactly, yeah, that's so. So that's an unsolved problem, okay? So what we do is we simply sort of construct a particular solution and declare that that's sort of the right one. And about this solution, we make an assertion, okay? This solution, and I come to this construction, it's based on the Kohl-Hopf transformation, but you cannot plug it into the equation and sort of assert that it's a solution of the equation, right? Okay, so now let's do what I was proposed to do. Okay, so now I do first the exact solution, and then, you know, there was sort of an observation which goes quite some time back by Bertini and Giacomin. Somehow nobody really listened to, but now, you know, in retrospect, I mean, this was actually a very, very sort of you know, very nice and sort of you know, advancing paper. And what they pointed out already, and of course which is confirmed by all these kind of things, is that the KPC equation becomes exact in the case of weak driving. And that's really something which is has not been understood by the physics community at all. You see, they were always talking, I mean, the argument which I showed you, you just add something and then, okay, so it was sort of more like another model. But the point of their observation is, and I will sort of explain this a little bit more, is that the KPC equation should think sort of as an approximation which becomes exact in the limit of weak driving. Okay?
If you knew how to regularize it, if you knew how to solve the thing with a regularized
Yes.
point, then you wouldn't have this problem, would you?
Well, you still at the end you want to, no, I mean, okay.
This is my question. If you compute expectation, do you in the end show, after all those determinants of these Fredholm determinants,
Yes.
they satisfy a nonlinear ODE's?
I don't think so. No, I don't. In fact, we don't know whether they satisfy any simple equation. Yeah,
If
yeah.
you take this with random matrix theory, those things always satisfy
That's right.
pain of A type thing.
That's right. Yeah.
So
Yeah.
that's why I was if you can just verify.
This bit right. I mean, so I mean, if you that's perfectly correct. I mean, if you look at the Tracy-Widom and then you find sort of solution of can represent this. So you could ask, you know, when I do this finite time correction from this equation, whether there's some differential equation which is satisfied. I mean, both groups have not found anything. Okay. So let me see. Just want to make clear. You see, there are two parts. I mean, just to make this clear. I mean, one part is simply to construct a mathematical object on which you can make an assertion, right? That's fine. The second part is to actually, you know, make an explicit assertion like the one in the theorem, right? And these are sort of two, you know, I mean, two different type of things. And so I sort of have to explain you each one of them a little bit, okay? Okay, so now the point is that you introduce what I like to call a partition function. So that's the exponential of the height. And then you realize that this partition function satisfies the stochastic heat equation. When you now look at what corresponds to the sharp wedge initial data, you see it just corresponds that we have to look at the fundamental solution of this equation. So the initial value will be just a delta function at the origin. Okay. Now, you solve this equation by introducing this an auxiliary Brownian motion, which in the physics literature is always called a directed polymer. And then you just sort of plug this in, and then you find this as a sort of integral formula, an explicit formula for the partition function. Of course, it's a random partition function because I still have all the randomness sitting here. The expectation is only over the Brownian motion. Okay, and in this language, it's called point-to-point because, you know, I'm starting at 0, so that's this point, and then this Brownian motion has to go up to the point x. That's this one over here, and it's sort of moving in this white noise random potential. And of course, this random variable up here doesn't make any sense, right? I mean, I just cannot integrate white noise along a Brownian motion. Okay? So now we have to do something, and there are various things to do. The one which I like best and which actually gives you the strongest results is that you do the most naive thing. I mean, you just start expanding the exponential, okay? And you do the average over the Brownian motion. So you see here I have this multiple w's. I mean, they're just sitting there. I mean, you can think of them at the moment as smooth functions. I mean, it's just sitting there, but I do the average over the Brownian motion. Therefore, I will get sort of the multipoint transition probability for Brownian motion. Okay. Well, now you want to make sense out of this thing, and then you remember, you know, a little bit of stochastic analysis, and then you say, okay, let's simply view this as a multiple Ito integral, which sort of course, corresponds to, you know, particular sort of discretization of that expression. Okay. And the main point about this about the Ito integral is something which is called the Ito lemma. Namely, you can easily, once you do this particular discretization, you can easily compute what is the L2 norm of the object, you know, when you sort of take the discretization, go to 0. Okay. Okay, so I haven't written this down, but what you can then check is that in fact this random variable is a well-defined L2 with this particular interpretation of the W is a well-defined, you know, square integrable random variable with respect to white noise. And from this,
can you also do this local times?
No, you just do it directly like this. And then from this, you can conclude that this object is strictly positive, almost surely. I mean, it has continuous sample path, and when you compute the expectation of this object, you just find what you might have thought before, namely, it's just the Gaussian transition probability for a Brownian motion. Okay. Of course, what we really want to do is don't want to compute the expected value of the partition function. We want to say something about the logarithm of the partition function. So you see that.
All difficulty lies.
Yeah, that's right. So you see, I mean, that's sort of one of the things where, why people were, in the early times so much interested in this topic. I mean, independent of the physics, it's sort of, it's sort of a standard example of disordered system in statistical mechanics. Of course, of a special flavor, so to speak. Okay. All right. Now let's see. Okay, and then so here's sort of the way how the construction goes. I mean, now once you have defined this partition function, you take the logarithm, and then I mean, that's a well-defined operation, and then now this is the object. That's the Kohl-Hopf solution which we study, right? Okay. All right, and now let me sort of, when you look at, now let me go back here. I mean, when you look at this, I mean, then of course, if you have a little bit sort of, ever looked at such things, I mean, it's sort of obvious, what else you want might to do. So, I mean, Tom mentioned already that you could color the noise a little bit, and then all these things are perfectly fine, and then you have to let, you want to make the limit to white noise. I mean, so you have to do a little bit of work for this. Or, of course, you can do even more drastic things, and you just replace this by a discrete integral. And so let me just sort of do this a little bit. Yes?
What exactly, you say the connection to the Wasser from Bertini-Giacomini, what quantity in the Wasser do you look at?
So in the Wasser, well, you look at the height function, right? I mean, so that's just the integrated density profile.
So you look again at this growing surface.
We look at the growing surface. That's right. And then what means weak driving is in the Wasser means that so. Well, it's a Wiesig or weakly asymmetric simple exclusion. I mean, so you imagine that you have this surface like this, right? And so this is my x, and here sort of the height, right? And now what we argued before in the simple approximation was to say that we fill up local minima with weight 1, and then we just keep going, right? That was sort of the construction which I have on the other board.
And the asymmetry is?
Now the asymmetry in this language just means that you remove local maxima with another weight, and you call this weight you call p, and this weight you call q. Okay? Now if you make p equal to q so that you balance what you remove and what you add, I mean, then you get a model which you can analyze, you get Gaussian fluctuations, and that's sort of an equilibrium interface. Okay, and now you make it asymmetric by saying that you have, I mean, you add more than you remove, and so you look, for instance, at the case where p is larger than q, and then you get a net drift. Now the assertion is that, I think I've maybe some formula later on, but the assertion is that if I look in the weak driving, so that let's normalize things by pq is equal to 1, and so the symmetric case would be if each one of them would be 1/2. And so if you're just a small deviation from 1/2, then you are very close to the KPC.
So you must, a small deviation, you scale time.
You scale time, you scale space, yeah, you have to do everything, right? But the main point is that, the starting point is that you want to look, I mean, you first decide that you want to do a weak driving, and then you have to look at the correct space-time scale where you see something, right? I mean, so that's fine.
That's, I guess, non-trivial.
Yeah, that's not trivial. But this observation is already due to Bertini and Giacomini. I mean, they wrote down already what is the correct limit and actually proved. I mean, they couldn't quite do the delta function because we're not even thinking about it, right? I mean, they started with some smooth profile, but this is what they did already. Okay, so now let's see. So I'm getting here out of space. So let's see, what should we do? Well, okay, so I don't want to overdraw. So presumably what I will have to do is I will have to sort of stop somewhere here in the middle. Anyway, so I will try to make a decent finish here. So so let me just say one thing. I mean, so I mean, this I think sort of also illustrates maybe better, what I mean, another way of looking at this weak driving. So let's assume that I simply discretize this integral completely, right? I mean, so now I put so my white noise I just replace. So the space-time continuum I replaced by a two-dimensional lattice, And the W's, I just replace by independent random variables, okay? I mean, they could be Gaussian, but I mean, let's just replace them by, with some moment condition. Anyway, let's just replace them by independent variables. And now I look at the partition function. Well, you see and I also discretize my Brownian motion to, upright past omega, which then sort of moves along like this and starts here and has to go to the point n, right? And the energy of this path, I just sort of sum the independent random variables along the path. So this is what I did over here, right? And so here you have exponential of that is the e to the omega. And then I smuggled in the beta. The beta controls, how strong the randomness is. So if I take beta very small, means that I'm sort of sitting in a random environment, which is sort of fluctuating a little bit, right? Okay. Now here's.
Have a minus sign?
Well, okay, yeah, you can. It doesn't make any difference. I mean, because you can absorb the minus sign into the e. I mean, it's fine. I mean, yeah, that's right. No, okay. It's good to know that there are some sign conventions. I mean, okay. Okay, so now the theorem is the following: that when I take the weak noise limit, you see, when you do in other cases weak noise limits, I mean, very often you lose properties of your system, right? So you might be worried here. So the weak noise limit means that I want to make this random environment just very, very mildly fluctuating. So I'm going to beta equal to 0, infinite temperature limit, okay? Now I have to balance this by, I want to see some effect of the randomness, right? I mean, so I have to balance this by making n sufficiently large. And then you have to do a computation. You find that the correct balance is that the beta to the power 4 times n has to be equal to 1, okay? And then the theorem is that if I now look at this partition function here, so here I put, I sort of made everything sort of somewhat simple. So this endpoint is sort of a long diagonal, and it's this n which goes to infinity. So the endpoint is n times t. And then the assertion is that when I look at this partition function, it has a limit, and its limit is actually given by the Kohl-Hopf solution. So that's another way which I personally find, it's sort of looking at, of course you can think of the weakly asymmetric simple exclusion, but that's sort of another way of looking at this continuum equation. So the assertion is there's a high temperature expansion, or high temperature limit, which of course, from which I just pick the first non-trivial term. I mean, if I would do anything else, I mean, then either the limit wouldn't exist or would be sort of trivial, right? I mean, so I just sort of pick up the leading term, and it so happens that this leading term actually leads to the KPC equation. And when you look at from this point of view, it's much less obvious why you should maintain universal behavior, right? And, after all, you're looking at very weak noise, but the assertion is that you barely do. Okay, so if you do anything sort of anything, I mean, you're sort of just at the edge where you retain the information about the universal behavior. Okay, so let's see. Now comes the weak RCEP. I will not be able to tell you anything anymore because the time is over. And so I'm afraid that I will have lots of other interesting things to say. But let me just stop with 2 pictures. I mean, and a small riddle, which I will not resolve in such a short time for you. So what is plotted here is exactly this kind of thing for the case which I discussed over here. I mean, this is sort of the Johansson case. So that's the totally asymmetric. So it corresponds to this problem here. I mean, so let me just do it. So I do the sharp wedge, okay, and I start filling, okay? And then I'm looking at the height above the origin, so I'm just looking how much I have filled. And then it's just a numerical simulation. You do 1,000, I mean, sort of typically it has sort of 1,000, I mean, it's not very long. I mean, you do 1,000 time steps. And what is plotted is now the exact distribution at that particular time of the height above the origin. And you see it's still discrete because we're on the lattice and just have no more data point. But you see also that this is the Tracy-Widom distribution, beta equal to 2, that, even on that discrete level, I mean, you think it's a rather good approximation, okay? But what you should see is that it's an approximation which sort of, which is the dots are coming in from the right? I mean, it's a little bit displaced there. Okay, because it's n equal 1,000. I mean, I'm not at infinite time. If I do it for even longer times, I will get more and more dots, and eventually I will sort of get a perfect approximation of the Tracy-Widom.
Sorry, just so where is right and where is left? If I think about the right same way, so the left is towards the inside.
Yes, I mean that's good. Okay, let's see. No, I think for the it's the same orientation as if I look at the white edge of the random matrices. Yeah. Okay, and now I want to show you a numerical plot of the exact solution of the KPC equation. So this requires some efforts actually, and in fact now we have even better plots, you see, because eventually at very early times the solution of the KPC equation is like a Gaussian which is centered at the origin. And so yes, this is the Tracy-Widom. You see that's the latest time, and now we have earlier time. So you see that the distribution is actually it's actually shifting to the left here, right? So before it was coming from the right. Okay, now it's coming from the left. But eventually, the slope will decrease. Eventually, it must make the Gaussian, which is centered at 0. So we'll sort of actually shift back over here. Okay? And so you see that there's universality, but also some non-universality. I mean, this long-time approximation, according to the KPC, comes from the left, whereas in the TASEP, it comes from the right.
But you have a prediction what it is for a long time, right?
Yeah.
So you don't,
Yeah.
not just the infinite time, which is.
Well, I mean, that's, we have that's the exact solution, right? I mean, so, okay. So you see that whenever you talk about universals, I mean, you have to sort of specify a little bit carefully what quantity you're looking at, and while exponents in this case are universally, the way exactly how you approach the long time limit, I mean, the exact finite time convection will actually do depend on the model. Okay, so I guess that's sort of already the end of the story. So, one thing which on the level of the KPC equation we do not understand are the flat initial conditions. So if I just start with h of x equal to 0, so just flat, we just don't know how to do the analysis. Okay? I mean, we tried, but so far we haven't done. Okay? So there's a possibility to produce multi-point generating functions of the same type. I mean, that sort of work together with Silva. And then there's another, to my taste, sort of very exciting work by O'Connell, who does another discretization, which is so-called Glynn-Witt model. I mean, that sort of comes from statistics or sort of queuing theory. And what you do in this model is that you decide to discretize. I mean, you keep the time direction, discretize only in sort of the two direction. And then the directed polymer, what it will do is it will sort of stay here for a while, then it goes to the next line, stay for a while, then to the next line, etc. Has to end up at this point. And on each line, you have now independent white noise. And so you just sort of, sum up, little Gaussian random variables in this way. Okay? And the reason why it's exciting is that, this is a model which you can actually analyze, has been analyzed at 0 temperature, and it's, in this case, the height function is identical to the top line of Dyson's Brownian motion with n particles. So the parameter n is here this endpoint, right? I mean, so I go to the time t and I go to this point. And when you look at this object here and you look at the height for this point, then you will see that it's at 0 temperature, it's exactly like the top line of Dyson's Brownian motion. And the big achievement of O'Connell was that he could do this also at finite temperature. And what he finds is a relation to the quantum Toda chain. So, he makes connection to another slew of exactly solvable models. And, there's sort of other people who study this representation theory. I mean, all kinds of things. I mean, it's sort of a community in itself. But somehow it seems that, in this view, we see yet another connection. Okay, so I stop here. Thank you very much.